Hello everyone, welcome to TerradigmOrbital's presentation on the Shell's refueling system. I'm Ryan Krause and I'm with the Mission Planning and Analysis Subteam. TerradigmOrbital is a concept company created by the students at the University of Maryland Aerospace Engineering Program. This is a design review for the Satellite Health and Equipment Life Lengthening System, or SHELS, which is our entry in the 2020 RASC-AL competition theme 4, Commercial Cislunar Business Development Plan. TerradigmOrbital is divided into 7 different subteams: Mission Planning and Analysis, Avionics and Flight Software Systems, Power Propulsion and Thermal, Load Structures and Mechanisms, Systems Integration, Business and Finances, and the Refuel Board.
This is the concept of operations for the Shell system. It consists of 2 main hardware components. There's a propellant depot capable of storing both xenon and hydrazine in large masses in geostationary orbit, and propellant transporters that take these propellants and move them to the clients who will be refueled. The propellant depot is launched directly into geostationary orbit by a Falcon Heavy, and similarly, the propellant transporters are launched directly into geostationary orbit by a Falcon 9. We will also be considering the Starship launch system if it becomes available. The depot remains stationary in geostationary orbit throughout its entire lifespan. The propellant transporters are responsible for moving the propellants from the depot to the prospective clients. These refueling operations consist of a propellant transporter beginning docked with the depot, filling up on the next client's propellant choice, xenon or hydrazine, and then phasing through geostationary orbit to that client. When the propellant transporters reach the client, they will use our docking and refueling interface to transfer propellant to the client. And when that's finished, they'll retreat from the client and begin the phasing process back to the depot, and the cycle will repeat. The duration of this entire operation depends on the level of demand we are supporting, but at what we anticipate to be the optimal level of demand for a propellant transporter to support, we anticipate this process will take 120 days. As the depot progresses throughout its life, it's going to be emptied gradually, and before a depot is fully depleted, a replacement will be launched. The depot will be disposed to a graveyard orbit 300 kilometers above geostationary orbit. The duration of a depot's lifespan also depends largely on the demand. Earlier on in the business, when we are anticipating a lower client base, the process could take up to 7 years. But as the client base expands, we're expecting that to be brought down to almost 2 years.
The 2 primary components of the Shell's refueling system are the propellant depot and the propellant transporter. The depot will be in geostationary orbit along with their customer base, and will have a wet mass of just under 15,000 kilograms when filled. It will store both hydrazine and xenon propellant. The ratio of these 2 will be determined by 2 things. One is the relative usage of these propellants by satellites in geostationary orbit, and 2 is the approximate amount of life extension each of these propellants can get a given satellite. There are advantages to having 2 separate depots for hydrazine and xenon, but doing so would incur a higher development cost up front. Additionally, a purely xenon depot would need to last a very long time in orbit because satellites don't need that much xenon for sufficient life extension. Our current model has a design lifetime of 7 years for the depot because we don't anticipate customers needing much more time than that to deplete it. The propellant transporters will be used to phase between the propellant depot and the customer satellites, delivering a specified amount of propellant. It has 2 configurations, one for hydrazine delivery and one for xenon. When delivering hydrazine, the xenon tanks will be empty, but when delivering xenon, the hydrazine tanks will still store at least 15 kilograms for its own maneuvering. It has a dry mass of just under 700 kilograms and a design lifetime of 15 years. When considering the parking orbit for the depot, we had to take the approach that mass is money. Each extra kilogram that can be delivered to geostationary orbit represents mass of propellant that can be sold to customers. So this decision was made in tandem with the launch vehicle selection. This comes with a trade-off. The lower the orbit, the more mass a launch vehicle can deliver to the parking orbit, but the more mass is going to be expended by the propellant transporters phasing to and from the parking orbit and geostationary orbit. This is a table that breaks that down for us for 6 candidate orbits that a SpaceX Falcon Heavy launched from Cape Canaveral could easily get into. The first 2 rows represent how much hydrazine propellant could be delivered to a parking orbit by the Falcon Heavy. The third one represents how much mass is going to be totally depleted per given operation. So this added together the amount of propellant that's given to a customer, as well as the amount of propellant that's used by the propellant transporter phasing to geostationary orbit. As we can see, Geostationary orbit, which is where the customers already are, represents the best parking orbit for the depot. In order to get these components to geostationary orbit, the Falcon family was selected for our launch vehicles because of their high reliability, high lift capacity, and low price. The depot will be launched on an expendable Falcon Heavy because at the moment it is SpaceX's largest lift capacity vehicle. Once we reach a demand level where having more than one depot launched in orbit at once is advantageous, which I'll be discussing in a little bit, we can then make a switch to Starship when that becomes available. As for the propellant transporters, we'd like to launch that on an expendable Falcon 9, and we'd like to launch it wet. That way it can service customers immediately upon getting into orbit. When launching wet, the Starship can fit 3 propellant transporters, 2 of which are fully wet, meaning with hydrazine and xenon, 1 of which is partially wet. And we're going to fill that one with xenon because xenon is more valuable to us per kg. The launch of the Falcon 9 will be adjusted to accommodate the given demand level.
Here you can see the list of RASC-AL requirements for the cislunar business development theme. You will notice across the top of each slide 1 or more of these icons denoting which requirements are covered in that slide. Many of the systems and system requirements are driven by this list of profit-generating requirements. The depot is designed to maintain the shell's propellant supply in GEO. Once the propellants are depleted, it is moved to graveyard and replaced. A single depot stores 8,500 kilograms hydrazine and 1,500 kilograms xenon. The transporter requires more robust navigation and maneuvering subsystems, as well as the pump and female interface of the refuel port system. The transporter's designed lifespan of 3 depots can make over 150 deliveries of up to 500 kilograms hydrazine or 150 kilograms xenon to an asset, while using 15 kilograms hydrazine or less for its own maneuvers.
And then so for the first topic, the general sizing requirements, we have to keep 3 payload fairings in mind: the Falcon 9, the Falcon Heavy, and Starship. And within these 3 launch vehicle payload, we have to keep in mind the limits of both mass and volume. And mass drives our profits, making mass a primary design factor for structural components. And if we use the entirety of the mass capacity for the launch vehicle payload, volume is no longer our limiting constraint because we would far exceed the mass limit before we approach the size limitations. And then for our propellants for the storage, we found out that composites would be the best choice, mainly because a significant weight advantage is customizable, higher pressure, better fatigue strength, and better coefficient of thermal expansion, high dampening capacity. And there's a few drawbacks in that they're a little more complex, and additional failure modes are to be considered with that. And then we designed like this matrix to decide what material to use. We went between S-class Kevlar 49 and T300 carbon, and Kevlar 49 won out. We end up having a higher transverse stiffness and strength, greater impact resistance, better radiation resistance, no moisture absorption, higher temperature capability, and there's just very few disadvantages to our choice that we found out so far. And then here's some of the numerical analysis for the Kevlar margin of safety. For the tensile strength, we had 9.92, and for the compressive strength is 3.3. And then I kind of skipped over the fuel depot, and now we're going to the propellant transporter. They will mimic the same design, we only have completed the propellant transporter so far, and we have a Gantt chart when that's going to be completed. But here's the FEA analysis for the trusses that are designed to bear the load for the propellant tanks for the propellant transporter. And so you can see here, this is like a 7G load during launch under the Falcon Heavy or Falcon 9, and it's within the safety margin. And on the right, that's it before the launch load. And then here's a finished CAD model of the propellant transporter. You can see the solar arrays, refuel ports, and communications, and the radiator. And then we did a plume impingement analysis and found out and moved everything so nothing would be impinging the solar panels or anything. And then we also went over MMOD shielding, and it is supposed to last for 15 years. And these are some of the things that we chose to to measure those, and this is a chart that we used, and some of the velocities that we have to be aware of while considering our shielding. And then here's monolithic shielding, and here's some of the different materials that we used and the densities. And we found out fiberglass is the clear front runner among the monolithic shield materials, lowest total mass, lowest wall thickness, and lowest cost.
I will start off by showing a summary of the power budget calculated from other components in our design. In looking at the communication and control systems, the propellant transfer method, and the propulsion systems components, the minimum required power to operate the depot is about 336 watts, and for each transporter it is about 420 watts. We then use these minimums to determine the required capacity and mass of the battery aboard each vehicle, as well as the sizing of the solar arrays needed to recharge them, as shown here. The type of batteries used for each vehicle is a lithium-ion battery with the following characteristics, derived from the source: high energy, long cycle life, and low maintenance lithium-ion cell for demanding applications. Depicted here are the battery models we will be using for the depot and transporters respectively. These values were derived from the minimum requirements specified in the power budget, as well as the feasibility for integration into our system. Depicted here is the power block diagram to represent the flow of power from the solar arrays to our batteries, then ultimately into our system. Since we are using hydrazine thrusters to execute maneuvers, we needed to design thrusters that fit the needs of our mission. We derived specifications for the thrusters by considering the minimum impulse bit required. We did the same process for both the 1 Newton and 20 Newton thrusters presented in the following slides. Depicted here is the 1 Newton monomethyl hydrazine thruster we designed, with specific impulse 220 seconds and an expansion ratio of 79.4. Depicted here is the 20 Newton monomethyl hydrazine thruster we designed, with specific impulse of 230 seconds and an expansion ratio of 61.8. When considering thermal effects, we first looked at effective operating temperature ranges for the components on our vehicles, as shown in this diagram. This allowed us to determine a required size for the radiators in the following slide. Considering absorptivity ratio and the heat required to radiate, the minimum radiator areas for the transporters and depot are 1 meter squared and 0.62 meters squared, respectively. Shown here is the multi-loop heat system consideration for our design. This factors in other heat sources such as solar radiation into the flow of heat for our system.
These operational flow diagrams of the transporter and depot illustrate both transfer directions using the depot to represent itself and the client asset. The designs incorporate both xenon and hydrazine. The hydrazine is used for the engines and delivery to the asset. The xenon is only for delivery. When delivering hydrazine, the pump is placed in a neutral state. Flow is managed by the regulator, and the splitter directs all flow to the hydrazine tank. The splitter on the other side of the system directs all flow to the RP system. The pressurant is kept at sufficiently high pressure to maintain consistent outflow, while the asset tank approaches its full state. For a xenon transfer, the splitter directs all flow to the xenon tank. The regulator is placed in neutral state, allowing maximum pressure to the pump, which then steps up the pressure to the required 151 bar, maintaining consistent outflow to the asset. You will notice that a bladder exists in the xenon tank, which is receiving a pressurant. This bladder-like tank exists to maintain consistent pressure as the xenon is emptied and the asset tank fills. The bladder creates a barrier preventing the pressurant and xenon from mixing, and allows the transporter to completely empty the xenon without an additional pump between the xenon and the asset. The pump and regulator are fully reversible to extract the pressurant from the two tanks, pumping it back into the pressurant tank. This operation is performed during the refill stage while attached to the depot. The extraction, combined with the high pressure of the depot tanks, completely refills the transporter without a pump on the depot. The similar depot design has two deviations. One, the depot has no need for a pressurant return and is designed without a pump, reducing mass, power, and costs. Two, the lack of pump resulted in substantially higher pressures than the transporter to fully empty the propellant tanks as the depot is depleted. Here we have a summary of the transporter tanks. Up top is the material, a composite Kevlar COPV used for all Shell's tanks, followed by the diameter of the transfer valve, the pressurant, and products available. Next is a table of values with the mass of each tank, the maximum fluid mass, and the respective pressures maintained in each tank. The bottom table lists the differential pressure required to transfer the propellant within the operational time limits of 12 hours and 60 days, respectively. The differential pressure was also used to determine the separation force during operation and calculate the coupling magnet's adhesive forces. To ensure a suitable coupling mechanism that would last over 21 years and to create a fail-safe mechanism that is easy to control, permanent electromagnets, or PEs, are used to couple the transfer valves. PEs are permanent magnets that are designed to accept a current which effectively shuts off their adhesive force while power is supplied. These types of magnets require little current and generate little heat, and only during decoupling procedures. They are also highly customizable, allowing for the specific adhesive forces required by our system. The pressure differential calculated for the transfer operations was used to determine the required adhesive force of the PEs. The second table shows the adhesive force, mass, power requirements, and dimensions of each sample PE. These sample PEs are off-the-shelf products that most closely match the adhesive force required. The mating of the two interfaces presents the PEs within attractive range of the metallic discs, and the PEs connect the two valves, holding them in place during the transfer. Here is the exploded view of the female refueling interface. The locking mechanism comprised of two rotating plates, motor, transfer valve, and PEs. The female interface is mounted to the transporter and houses all power, motors, and actuating systems, reducing the impact on the asset's design. The two conical receptacles decrease mating requirements for the male and female interfaces. The two PEs attached to the sides of the transfer valve are used during refueling operations to couple and maintain connection of the transfer valves, which contain poppets for flow control. The PEs and valve are seated in a contoured non-magnetic sheath, not shown here, in the cradle that allows the valve to translate perpendicular to the surface of the interface. The male refueling interface is a dumb system. It contains no motors, power, or actuation except the single poppet in the transfer valve. The male interface is mounted to the frame of the asset and contains a step valve to convert the line size of the asset to the transfer valve size of the refueling port system. Instead of PEs, the male interface contains metallic discs for the PEs to adhere. This side of the coupling does not translate. The transporter is equipped with a separate refuel interface for xenon. Though essentially the same design as for hydrazine, the increased pressures required larger PEs. While the pin dimensions are the same, the size of the casing, spacing of the pins, and cradle had to be increased to accommodate the larger PEs. Inside each interface transfer valve is a poppet and spring designed to compress into the valve, opening a path for the propellant to flow. When the valves separate, the springs force the poppets back into place, sealing the valves and preventing leakage.
Before addressing the control of our spacecraft, we need to discuss the command logic. Position command is depicted here as follows. This is done through comparing the position at epoch with the desired position. Position gets fed as an input into the attitude command, and similar to the pose command, compares current attitude quaternion to desired quaternion. We use quaternions in this case to eliminate the possibility of gimbal lock with Euler angles. For both position and attitude, we make use of a PID controller, with characteristics shown here. The control logic, therefore, can be represented as the following block for inputs and outputs, where error is taken as an input and correcting commands are generated from the controller, as previously discussed in the command logic. In order to test the effectiveness of the controllers, we created a nominal simulation to produce performance plots. The simulation describes our entire sequence for a transporter moving to the safety ellipse around the depot, transferring to a target satellite, and then walking to the target in order to dock. Depicted here are graphs of the position and attitude error over the entire span of the simulation. Depicted here are the radial in-track and cross-track positions, as well as corresponding attitude error for the safety ellipse part of the sequence. Depicted here are pose and attitude error for the docking sequence with the target satellite. And depicted here is the actuation for the walk to the target as well as the docking procedure. The final component of the simulation involves the thrust cycles, which helps in determining which thrusters are appropriate by analyzing how much mass is expended, as well as comparing throughput for thruster models. For ground network capabilities, we decided to use near-Earth network facilities due to the number of ground stations they have available. Near-Earth network has 14 ground stations available with 33 different antenna design. Antenna aperture sizes range from 10 to 18 meters in diameter. Having access to near-Earth network's ground stations allows constant communication between our spacecraft and ground stations. The figures shown here and on the previous slide depict the line of sight from 3 near-Earth network ground stations to a propellant transporter as it would appear in orbit. In finding an estimate for the data rates for uplink and downlink connections, we calculated antenna size that would provide enough gain to support the power systems on our spacecraft, as shown by this plot here. We then performed a link margin analysis, a clip of which is shown here, to determine the best frequency bands offered by near-Earth network for use in both uplink and downlink communication. As determined by our link margin analysis, S-band will be used for uplink, and Ka band will be used for downlink.
Based on research, the current market size of GEO assets is estimated at 450. From research on future market sizes and a simple linearization of those projections, a growth of 81 assets per year was applied to the market to generate these projections. Since Shells intends to offer both hydrazine and xenon propellants, it is important to understand the share of each propellant in the market and how those shares are changing. The graph on the left shows the mild increase in the xenon share with a matched decrease in the hydrazine share. The graph on the right shows the total number of assets in the market, as well as the number of hydrazine versus xenon assets as the market grows and their market shares change. The market trends and growth projections were used as a basis for the company market penetration projection. An initial market penetration of 1% into the 450 asset market was used. From there, a linear 0.5% market penetration was applied to the growing market to project the number of clients and asset refuels over the course of 21 years. This graph shows total number of clients per year, the total number of refuels per year, and then the total refuels of each propellant per year. Here we have a buildup of our initial costs, our annual costs, and our discount rate. Across the top is the transporter development cost, followed by the production and launch of the first 3 transporters, the same for the depot, then the total. This total is our business development costs, which are the initial investment asked of the investor. The annual costs are yearly costs after launch and covered by the business, which is why they are not included. Next, we have the discount rate. As you can see here, there are several factors involved in the buildup of the discount rate. Each factor was selected conservatively and builds a substantial discount rate of 37.7%. The discount rate is an independent value for investors to use as a measure of the rate of return, or ROR, which we will see later. The ROR should be at least equal to the discount rate to attract investors. These graphs project over the same 21-year period from first asset servicing to the retirement of the first 3 transporters. On the left is the revenue projection, based on the earlier market projections, market penetration projections, and estimated revenue of each asset serviced. In the middle is the annual accrual projections. These are calculated from the revenue values on the left, and then the depreciation and amortization of the transporters and depot development, production, and launch costs are deducted over the course of the 21 years. On the right is the cash flow, or EBITDA, earnings before interest, depreciation, taxation, or amortization. These values only subtract the yearly operational costs, which were not included in the annual accrual graph. EBITDA is the source of the ROR, ROI, and valuation. It is also where the payback period is calculated by summing the years until the initial investment has been met. The colored columns make it easy to see the location of the 5-year valuation, the end of the payback period, and the first billion-dollar year. The far left table shows the buildup of the 13-year total payback period, the development period of 5 years, plus the payback period after first asset servicing of 8 years. Here we see the annual accrual and EBITDA values for each of the 21 years using the 4.65% charge of the assets estimated $200 million per year revenue. The EBITDA column is used to calculate the table values on the left. Total cash accounting, ROI, ROR, and valuation. Total cash accounting is the sum of the 21 years of EBITDA values. This $10.23 billion is then used to calculate the ROI, which is the total percent return an investor could receive if they owned 100% of the company. The ROI is then divided over the 21-year period to obtain the ROR. Recall that the ROR is what investors compare to the discount rate and must be equal to or higher than the discount rate of 37.7%. As can be seen, there is an 11% margin between the discount rate and the projected ROR, which should be attractive to investors. Lastly, to obtain a valuation, it is important to determine the appropriate multiple of EBITDA to use. After reviewing data on aerospace and other industry EBITDA multiples, aerospace appeared to have an average of 12, while other industries rested around 6 to 8. It was decided to use a conservative multiple of 8 to complete the valuation. Taking the amount from year 5 of the EBITDA column and multiplying it by this nominal 8 times EBITDA, the year 5 valuation is found to be $1.21 billion.
As of today, there are around 450 or so satellites in geostationary orbit, of which 25 to 30 get decommissioned each year. So here's a quote from a Northrop Grumman executive essentially explaining that in the coming decade, the life extension market for geostationary satellites should be above 150 satellites. Now, when considering our competitors, we also have to consider robotic servicing because that's also in the life extension market. In low Earth orbit, RASC-AL is set to do some robotic servicing, but in geostationary orbit, we have RASC-GS. Now, they recently had a contract that was terminated last year with a company to provide them with a satellite bus. This contract was recently awarded to Northrop Grumman. That's significant because Northrop Grumman has the mission extension vehicle, which latches onto customers and provides them life extension that way. And they just had their most recent Intelsat dock this year. They charge around $13 or so million per year. The current contract with Intelsat is set to last for 5 years, so $65 total million for 5 years of life extension.
Hello, I'm Patrick Haney. So how does the Shell system distinguish itself from its competitors? First is the large storable propellant depot, which is critical to the system. The affordable high-capacity launch of Falcon Heavy enables storage of a large propellant mass in space where it is most valuable. Business is made possible because of the low price per kilogram enabled by Falcon Heavy. We also have the standardized dedicated refuel port. The port is designed for low-risk, streamlined refuel operations on orbit because the hardware supports transfer of propellant and pressurant, aids in docking, and enables a secure mechanical connection between the spacecraft. Other systems rely on hardware not originally designed for in-space operation, and this increases risk. With our system, the client leaves with intact hardware and fully independent operations. The Shell system also enables proactive servicing. Competitors are entirely reactive. They're designed for uncooperative systems on existing satellites. On the other hand, Shells will plan and design for servicing from the outset of satellite manufacture, enabling a new paradigm of easily serviceable satellites for low cost.